Welcome to Off-World Resources. So here we're going to look at how we can get resources and what sort of resources we can get from places other than Earth. So if we start traveling into space, what kind of things can we find? So firstly, did you know that China is considering the possibility of mining the moon? The barren lunar landscape is thought to contain ores, which if you remember from the previous lesson are the bare natural way that we find a lot of these metals. So not all of them things like gold and stuff we find and they're good to go, but a lot of the others, steel and iron and things like that, are found as an ore that we then have to refine. So it's thought that a lot of these rare metal ores are contained in the moon, and they're really difficult to extract on the Earth. So we could use some of our modern technology to go over to the moon and basically mine it. And this is, something that they're genuinely considering, and this is something that we may do in the future. Let's say we wanted to venture out into the vast expanse of space, and we wanted to harvest these resources. How long would it take just to get to the closest planet? Here are some average numbers for you, and before I put that up, does anyone know what is the closest planet to us? In case you've forgotten, there's a nice little jingle, and you can remember it as my very easy memory jingle seems useful naming planets. So that goes, my very easy is Mercury, Venus, Earth. Memory jingle, Mars, Jupiter, seems useful, Saturn, Uranus, naming, Neptune, and then planets, it would be Pluto, but Pluto is technically not a planet anymore, so it would just be useful naming and stop there. But let's say we want to go to the nearest one. Here are some average numbers for you. So looking at this is the average time that certain spacecraft have taken. So this was the craft that made the trip, this is where it went, and this is how long it took. So if we wanted to go to the moon, you're looking at about 3 days. That was what the Apollo mission took. It took 3 days just to get to the moon. So that's a long time. That's just to get to the moon. What about if we go to the nearest planets? We've got 15 months to Venus, 11 months to Mars, which is what we're looking at the moment. Vesta and Jupiter, 4 years, 6 years to get to Jupiter. Mercury, 6.5 years, Saturn, 7 years. And these, depending on, again, different spaceship. This is Voyager 1, 13 months, a few years, 8 years, etc. And then Pluto, 9.5 years. So you imagine that we want to go harness Mars. It takes you 11 months just to get there. Then you've got to mine it, then you've got to travel back, and that takes you another 11 months. So you're looking at almost 2 years in travel time alone, let alone how long it takes you to get there or to actually extract the resources. So it's an extremely long time to be traveling purely for a resource. So how would this actually work? If we wanted to mine the moon, what would this actually look like, and how would we go about it? This is a document from NASA, from their Jet Propulsion Laboratory, and this was basically a concept of how they would actually do it and what we would get from it. So first thing to consider is, why would we mine it? So from our geological surveys, so the analysis of the ground and what's in it and things like that, the moon contains 3 things. It contains water, which is obviously essential. We talked about that in our most important resources. It contains a lot of helium, which apart from being able to blow up your balloons and have sweet parties, it's actually an element used for future developments in the energy sector such as nuclear fusion. We need a lot of helium for that. So it's going to be a very important element. It also contains a lot of rare earth metals. So if you see this word REMS, or REM, it stands for rare earth metal. So that's an important word. Maybe make a note of that in your book. The REM is rare earth metal. So this is basically just a type of metal. It's an element, but these are the special ones. These are the really hard to find, very valuable kind of ones. And so an example of that is scandium and yttrium. And these are used in modern electronics, and they're mostly produced in China. So we need these rare metals to be able to produce your phones and your computers and things like that. So over here we're talking about those REMs again. Remember, rare earth metals. So 90% of the world's REM supply is produced in China. 90%. So the problem with that though is that 15 to 20 years is how long China thinks that its reserves will last. So in 15 to 20 years, China is going to run out of these rare earth metals. And they're producing 90% of the world's amount. So that's a really big problem. So we need to figure out another supply in 15 to 20 years, and they think the moon might be one of them. So how would it work? So there's a couple of different phases. At this stage, They're kind of using the underpants gnomes as business model. Phase 1, go to the moon. Phase 2, Phase 3, get minerals, make profit. Spacex, which if you haven't heard of that, is another space organization similar to NASA. They're trying to solve the problem of the launch costs. So obviously that's an issue. It costs a huge amount of money to build a rocket, send it into space, and they have designed and tested a lot of reusable rockets that they can basically return, and we can reuse the whole thing and try not to waste materials. 3D printers are going to be very important. So moon mining is going to require infrastructure before it can even begin. And people can't live on the moon, so we need a way to get up there and build houses, build facilities and things like that. And if you have a look on YouTube, there's a whole bunch of videos of these huge 3D printers that build houses, and they build like different shapes, and they build these like little igloo domes and things. And that's a really cool technology that's out at the moment. So this might be the way that we do it. We also need a way to store the helium if we're going to extract it. So if we want to ferry or transport vast amounts of this soil to Earth to process it, that's just not going to be feasible. Soil is heavy. We need huge, huge volumes of it. We're not going to just cart dirt back to Earth to refine it and then just get rid of the useless stuff. So we need a way to actually extract that gas on the moon. So we're going to need these big industrial facilities on the moon. Rather than pay people to go up there and struggle to live on a planet that has, or a satellite in this case, that has no atmosphere, no life, anything like that, it's going to be easy to have robots. So we'll have a whole bunch of robot miners that'll go and they'll dig the soil and they'll do all this stuff for us. And given that we've got water there, or potentially have that water, we could potentially set up this base. So we could have the lunar base, and this is sort of a long-term process. If we're going to be there for a long time, we can set up the lunar base, we can have people living there, and we can use the 3D printers that we talked about earlier to build this. Then once it's all done and sealed and we can put oxygen in it and supply water to it, then people can go up and inhabit it. Obviously this is a big concern. What effect is it going to have? If we start harnessing the moon, is it going to affect us? If we, a lot of people have said, what happens if the moon would blow up and things like that? And this is kind of a similar situation. If the moon has a mass of 37 Q tons, so challenge for you, have a look at what Q means. What is the symbol Q in terms of tons? How many tons is that? So some of the calculations are suggesting that if 1 metric ton was removed entirely from the moon each day, so we remove an entire ton every single day, it would take 220 million years to deplete 1% of the moon's mass. So that's 1 ton. That's not really a huge amount in terms of, you look at what our mines in Australia are digging out, and it's much, much more than that. But on average, if we're digging out a metric ton every day, it would still take 220 million years before 1% of that mass is depleted. And this is not going to be enough to cause any difference in the orbit or change our tides or our waves or anything like that. So really, it's very insignificant. What about things like environmental and ethical consequences, though? This is an important thing. So we need to consider the impact on future generations. How is this going to affect them? And it could be a whole range of things. So it'd be great for you guys to think about how this may actually affect people and affect future generations. We also need to think about the importance of the moon's role in human culture. So there's a lot of religions and a lot of stories that are based around the moon. The moon is quite a sacred thing to some people. We obviously need to consider this fact. It's a bit like having sacred land in Australia that, people have a very spiritual connection to, and we've dedicated that so that no one can tamper with it. The moon is kind of the same thing, but no one owns the moon, and that's a whole different debate. Then you've got things like the stakeholders in the lunar heritage. So who is actually making the money from it? Who has a claim to the moon? And can any country just go up there and start harvesting the moon? It's a very grey area on the legalities or the legal factors involved in this. And obviously the visual impact. So what's the moon going to look like if we start digging big holes in it? Is it going to change how bright it is at night when we have a full moon? Or is it just going to start to look ugly and we no longer have this kind of attractive thing in the sky at night? That's all things to consider. So according to the 1967 United Nations Outer Space Treaty, no one can claim ownership of the moon. So even if you were the first one there and you've harvested and you've got the biggest factories and whatever, you cannot claim ownership. That's this big treaty that all of the worlds have agreed to, that no one will ever own the moon. Some of the space law experts, however, are questioning whether this could prevent private ownership. So a nation can't claim it, so no country can say, all right, America owns the moon now, but there is a bit of a grey area there as to whether a business or a company could go up and claim that they own this part of the thing. So there's currently nothing to stop the miners claiming it as a commercial venture, which just means it's their property, they're extracting resources from it. Really, until we get there and we actually start mining, we're not really going to know. We need these things to happen before we can sort of react to them, unfortunately. So let's look at some off-world resources in terms of what is available in different places. Remember REMs before we talked about rare earth metals? Another acronym is a near-earth object. So they call these NEOs for short. So a NEO is a near-earth object. This is any smaller or small solar system object whose orbit brings it close to Earth. So basically anything that's whizzing around Earth and at some point it comes quite close to us, we consider that a near-Earth object. If its orbit crosses the Earth and the object is larger than 140 meters across, which is pretty big, it's considered a potentially hazardous object, so a PHO. These words you don't need to know. But anything that's 140 meters across and comes near Earth is considered potentially hazardous, so it could be dangerous to us. Most of these things, the PHOs and the NEOs, are asteroids, but a very, very small amount of them are actually comets as well. There's over 20,000 known near-Earth asteroids and 100 short-period near-Earth comets. So 20,000 asteroids and over 100 comets that we know that come relatively close to Earth. That's pretty significant.
Some say humanity's future as a spacefaring species is just around the corner. But realistically, how are we going to get there? The answer is asteroids. These seemingly unimpressive lumps of rock could actually be the intergalactic pit stops for exploring the universe. They have the potential to become cosmic gas stations and the building blocks for habitats on Mars, to change how we navigate through space and even to revolutionize earthly engineering and economies. But their potential remains untapped.
We call the asteroids the stepping stones to the solar system, and we live in the age where humanity will make the leap into space.
So how close are we to mining in space? Scientists and entrepreneurs want to mine asteroids because they can contain metals and water, rare minerals, even elements that are impossible to form on Earth. They're huge, they're everywhere, and while they all sort of look like your average space rock, there are some key differences between each type that determine which one to mine first. From the outside, the one with the most gold rush potential would seem to be metallic asteroids, made of nickel iron, that may also contain valuable metals like palladium, platinum, and of course, gold. But don't be fooled. The real jackpot here is the carbonaceous asteroids, which might just contain the most valuable resource of all, water.
Before we go after the minerals for mining purposes, the first thing we need to do is learn how to extract water from asteroids. Water is going to be like the oil of the space age.
A water source in our planetary neighborhood would be like a space oasis, a source of hydrogen and oxygen for rocket fuel and life support systems, a tool to shield us from radiation, and even a source of drinking water for astronauts. The problem is, finding these C-type asteroids is tricky.
The carbonaceous asteroids are extremely dark, darker than a blackboard, darker than freshly laid tar. How do you find those? All that sunlight they don't reflect gets absorbed, warms them up, and they glow in the infrared.
That's why scientists at NASA's Jet Propulsion Laboratory are developing the Near-Earth Object Camera, or NEOCAM, which, in addition to identifying potentially hazardous near-Earth objects, will be able to comb the infrared for evidence of C-type asteroids. Okay, so we can identify which rock to target. Now, we just have to figure out how to get a piece of it. While a number of space probes, like Hayabusa 2, are working on this right now, they're still just at the sample collection phase. What we need to know is how to successfully mine an asteroid. Nets, harpoons, augers, and even a giant magnetic rake have all been proposed. The problem is, traditional mining methods rely on the application of force, which is a challenge in low gravity.
If you saw the movie where Bruce Willis saved the Earth by landing on an asteroid and dropping atom bombs, that's really problematic.
A lot of these asteroids are just piles of rubble, and they're held together by microgravity, 1,000,000 times weaker than gravity on Earth. If you hold onto a rock, you say, I've landed on the asteroid, and you pull on the rock because you're trying to drill in, it'll come away, right? And then the next one will come away, and then the next one. What are you actually going to hold on to?
One Zen answer, nothing. At least that's the idea behind the approach that Dr. Sercel and his team at TransAstra are developing, dubbed optical mining.
What we do is we take large, very lightweight, thin-film solar reflectors, concentrate large quantities of sunlight into small areas. When the sunlight hits the surface of the asteroid, it causes a thermal shock that breaks the surface and drives the water and other valuable volatile chemicals out. That process of driving the volatiles out actually cleans the surface so that more sunlight can drill holes in the surface. We don't even have to touch the surface of an asteroid to dig holes in it.
This ant in a magnifying glass technology sounds like some kind of sci-fi laser ray gun, but it's real. And Joel's team is about to start testing the next phase using the world's biggest light bulb and synthetic asteroids at the Colorado School of Mines. And with continued support from NASA, their experiments are generating some buzz. But what then? What do you do with a bag of vaporized space rock?
A clever idea that TransAstra is developing is that they will go to an asteroid and use some of the water that they mine as propellant to come back.
If we can turn near-Earth asteroids into gas stations to refuel spacecraft, that has a tremendous effect in reducing the cost of human exploration.
And the propellant thruster that TransAstra is developing channels one of the most industrious creatures in the animal kingdom.
Just as honeybees harvest nectar, and they use then the energy of the nectar to power their civilization, the Apis architecture harvests water and other valuable materials from the asteroids, and then uses those materials with sunlight to power space industrialization and settlement.
First, TransAstra will launch Mini-Bee, a small demonstrator vehicle to test their method on a simulated asteroid in low Earth orbit. That can prove that optical mining works in space. A larger craft called the Honeybee will follow. And with the help of tug vehicles they call worker bees, they'll pave the way for the Queen.
The Queen Bee is the ultimate asteroid mining system. It's designed to fly out to an asteroid that might be 100 feet across, capture that asteroid in a giant enclosure, and then mine thousands of tons of water and other valuable volatile materials from it. A small fleet of queen bees will create a large ecosystem of water and other valuable materials in Earth space that will make it so that private venture can afford to build hotels on the moon. And ordinary citizens will be able to fly into space, aggregate their resources, and build space settlements out of asteroid resources.
But hold your horses. Or bees, I guess. This sounds like we're getting back into that gold rush territory. And what we don't want is to completely deplete the resources on Earth and then do the same thing in the solar system. That's why Dr. Elvis is fighting to preserve the majority of our solar system as wilderness.
We're very bad at looking ahead and seeing the consequences. We need a warning bell, a tripwire, saying if you've got to this point, you may not think it, but you're very close to finishing the entire resources of the asteroid belt.
So let's just say we did preserve most of the solar system's untrammeled wilderness, like 7/8 of it. What would that leave us with?
1/8 is only 3 steps away from complete exhaustion of the solar system's resources. And if we stopped at that point, we could keep that going for thousands of years.
So once we find the right asteroids, all we have to do is capture them, blast them with highly concentrated sunlight, catch their debris, and use it to propel insect-inspired spacecraft onto their next stop, providing the ultimate cosmic gas stations for humanity's highway through the solar system, all while preserving the wilderness around that highway so that our intergalactic future doesn't burn out before it even starts. Wow, sounds like a lot of work. So how close are we to mining in space?
In 10 years, we'll be launching our first asteroid mining vehicles to go out to asteroids and bring back substantive quantities of resources.
In 100 years, it's quite plausible that there will be people living on the moon in giant structures made of iron and so on, which will come from the asteroids, most likely.
What we know about life is that as life evolves, it fills whatever ecological niche or system it has. And then it finds a way to jump to the next level. Just at the time when we have the technology to make the leap into space, this is as significant a moment as when fish came up on the land.
If you think the future is gonna rock, check out more episodes of How Close Are We on this playlist. And for more epic science stories, be sure to subscribe to Seeker.
Okay, so looking at some of the materials that we can get off asteroids, this diagram here shows you an example of some of the different materials that are available. So looking at the element abundance relative to the Earth's crust, we're talking 17 times more hydrogen, 75 times more carbon, 74 times more nitrogen, and about the same amount of oxygen, 1 times the oxygen. We've also got things like iron, copper, nickel, ruthenium, rhodium, palladium, osmium, iridium, and platinum, all extremely useful. And there's some examples here from catalytic converters in the cars, LCD screens, building advanced materials, cancer treatment, etc. So these are very, very usable and valuable resources. This gives you a bit of a representation of what each planet contains within our solar system. Looking at all of the planets, here is us right here, and you can see we've got inner core, outer core, mantle, and the surface. And then you look at some of the other planets and what they're made of. So for us, it's rock and silicates. And then we got our surface. In Mars's case, there's a huge amount of iron and nickel in the core. Jupiter's case is mostly hydrogen and hydrogen gas. More hydrogen, metallic hydrogen, a lot of water, hydrogen gas, water, rock silicates, etc. So you can see some of the different compositions, and you can see how thick these layers are. So in these cases, these are mostly gases. So hydrogen gas, this has water. This is virtually a gaseous planet. Huge amounts of hydrogen. And then we go into things like Mercury, which is mostly rocks and iron, but extremely, extremely hot. So not inhabitable at all. Now that you've finished this video, have a look at the quizzes link that is available. It's all about interesting facts about space. So this is not necessarily stuff that you need to know. It's just a bit of a trivia quiz about some fun facts about space. And this is our off-world resources.